In today's tutorial, we are diving into the fascinating world of compile-time functions in Zig. We'll explore how leveraging the comptime keyword enables developers to perform computations at compile time, enhancing efficiency and safety in programming. So far, we learned about advanced type coercion techniques in programming, focusing on how implicit and explicit conversions of types can improve code efficiency and reduce errors. We covered examples in Zig illustrating mpyanev type resolution, coercion in function parameters, and automatic coercion with arrays and slices. We also explored the use of protocols, structs, and generics in relation to type coercion, highlighting their significance in creating flexible and robust code. Our journey emphasized the importance of testing to ensure proper coercion behavior in various scenarios. Now we will talk about compile-time functions and we'll discover how they can help you write more efficient and safe Zig code. Now let's take a look at a practical implementation of the comptime keyword in Zig by writing a factorial function. In this code, we define a function named factorial that takes a non-negative integer n as input. The striking feature here is the comptime modifier applied to the function, which instructs the compiler to evaluate the factorial value during compile time, ensuring that the result is computed before the program runs. This recursive function follows the standard definition of a factorial where it multiplies n by the factorial of n1 until it reaches 0, at which point it returns 1. Next, we proceed to the main function where we call factorial 5. Since the computation of this factorial occurs at compile time, the output is determined before execution, allowing us to directly print the result. The use of std debug print here demonstrates how we can print the computed factorial value, which in this instance is 15. This approach not only highlights the efficiency gained from compile time calculations, but also emphasizes the power of Zig's comptime functionality in enhancing program performance and minimizing runtime overhead. Next, we will write the following code to demonstrate how to create an array with a constant length using the comptime keyword in Zig. The createArray function is defined to take a length parameter, which is marked as comptime u32. This indicates that the length must be determined at compile time, allowing the Zig compiler to allocate the exact amount of memory needed for the array efficiently. Within the function, we return an array initialized with zeros, where the size is specified by the compile time constant length. This enables Zig to optimize memory usage since the size is known ahead of execution. In the main function, we call createArray5, and as a result, the compiler creates an array of 5 integers. The use of len allows us to fetch the length of the array easily, demonstrating how compile time values can enforce safer and more efficient memory management. This code snippet illustrates the power of compile time function execution, enhancing performance by reducing runtime overhead. The explicit definition aids in type safety, ensuring that the developer has declared the array's size clearly and avoids potential runtime errors. Now let's see how we can implement a fixed array struct that leverages compile time capabilities in Zig. This struct contains a fixed size array of i32 integers where the array's size is determined at compile time. The primary function within this struct, initialize, takes an integer value and populates the array with that value. By creating an instance of fixed array, we gain a clear and strict interface regarding what can be passed and stored, ultimately minimizing potential runtime errors. The initialize function begins by creating an instance of fixed array and initializing the data field to an array of zeros. It then uses a loop to iterate through each element in the array, assigning the specified value to each element. This approach not only highlights the flexibility of struct definitions in Zig, but also demonstrates how compile time functions can enhance safety by ensuring that the array's size and contents are predetermined during compilation. In the main function, we call initialize with the value 42, and as we print each element of the array, we see that the array is effectively filled with this value, emphasizing the importance of compile time structure in both performance and clarity. Now let's take a look at the implementation of a compile time generated lookup table in Zig. This code defines a lookup table struct that leverages the comptime feature to generate an array of squared values. The generate function initializes a lookup table instance, where an array data of 10 unsigned 32-bit integers is created. During the execution of this function, a loop iterates over the data array, squaring each index and assigning it to the corresponding element. This computation occurs entirely at compile time, which means that by the time our main function runs, the lookup table is already populated with its final values, 0, 1, 4, 9, 16, 25, 36, 49, 64, and 81. This implementation not only avoids runtime computation, enhancing performance, but it also showcases the advantages of using compile-time functions for generating static data structures efficiently. Finally, the main function iterates through the lookup array to print out each squared value, demonstrating how this pre-computed table can be accessed at runtime without costly calculations. Now let's take a look at how to implement a generic max function that effectively demonstrates Zig's compile-time type capabilities. In this example, we define the max function, which takes a type parameter t specified with the comptime keyword. By declaring t as a type, we inform the compiler that it will be a fixed type when the code is compiled. This allows the function to work seamlessly with any comparable type, showcasing the flexibility that generics provide. The max function accepts two parameters of type t, and utilizes a basic conditional statement to determine which value is larger. This simple yet powerful design not only adheres to type safety, but also ensures that the correct implementation is generated at compile time for the given types. Next, we call the max function in the main function with both u32 and f32. The results reveal the correct maximum value for each data type. This approach exemplifies how Zig's generic programming features enable the creation of reusable components while optimizing performance through compile-time calculations. In summary, using compile-time functions in Zig can completely change the efficiency and safety of your code. By declaring variables and functions with comptime, the compiler can execute certain computations during compilation rather than at runtime. This not only enhances performance but also allows for greater type safety and more flexible programming paradigms. Zig's compile-time capabilities give programmers the tools to define complex types, generate arrays, create lookup tables, and build generic functions, powerful features in the toolbox of any developer. So we've covered a lot today about how the comptime keyword in Zig enables compile-time execution, allows for the creation of flexible and efficient code, and dramatically improves performance by shifting work from runtime to compile time. Now as you continue exploring Zig programming, keep in mind how you can maximize the use of comptime to write cleaner, faster, and more efficient code. Happy coding!